All right, hello everyone, and welcome to Lesson 7 for the AP Chemistry Unit 8 curriculum. Today we are going to be discussing pH and pKa and how they relate to each other and what they can tell us. At the end of this video, you should know that buffers resist change in pH when small amounts of acid or base are added. The relationship between pH and pKa is going to determine whether an acid is mostly in its protonated state, HA, or deprotonated state, A-. If pH is less than pKa, then your acid form is going to dominate. If pH is greater than pKa, then your base form will dominate. This relationship allows you to predict the protonation state of a substance in solution. And then indicators are going to change color depending on whether they are protonated or deprotonated, making them useful for detecting those pH changes. So acids and bases work by donating or accepting protons, and this depends on their protonation state. So a weak acid, or HA, can exist as its protonated form, HA, or deprotonated form, A-. So essentially all these words mean is, does it have a proton or does it not have a proton? Protonated means it does have a proton, deprotonated means it does not have its proton. The pH compared to pKa determines which of those forms is going to dominate over the other. So if pH is less than pKa, then you have more of your acid than you do of your base. If pH is greater than pKa, then you have more of your base than you do your acid. And with that comparison, it's going to let us predict whether an acid is going to hold on or release a proton in a given solution. All right, so brief review. Remember, pH measures the concentration of H plus ions. On your formula sheet, it is written as pH is equal to the negative log of the concentration of H plus or H3O plus ions. pKa is going to measure your acid strength. pKa is defined by calculations as the negative log of your equilibrium constant for your acid. So it makes sense that this measures the strength because we know if we have a very high Ka value, that means we're going to form a lot of ions. And if we are dissociating into ions, that means we have a strong acid. So if we take the negative log of that, that means we're going to have a very low pKa. So low pKa is going to signify that we have a strong acid. High pKa signifies that we have a weak acid. So for weak acids, pKa represents the pH at which an acid is 50% in the acid state and 50% in the conjugate base state. So 50% protonated and 50% deprotonated. So that should make sense that when the pH is lower than the pKa, we have more acidic solution. And when the pH is higher than the pKa, we have a more basic solution. So let's go through these values one at a time. So first, what is happening when pH is less than pKa? For me, the easiest way to kind of visualize this is using a titration curve with a weak acid. So here we're using acetic acid, which is CH3COOH. So you can see we're starting with CH3COOH. At the half equivalence point, we have equal amounts of acetic acid and acetate, which is our conjugate base. And then once we move past that half equivalence point, then we're going to predominantly have acetate, which is our conjugate base. Now, essentially what you have to be able to do through this lesson is if you know that the pH is less than pKa, then you need to know that you're going to have more acetic acid than you would acetate in solution, which means you're going to have a more acidic solution. Now we talk about our half equivalence point where pH is equal to pKa. And remember, in this region, our concentration of acid is equal to our concentration of conjugate base. So if this is when pH is equal to pKa, we know if we are increasing pH, we are moving to this section of the titration curve where we now have a higher concentration of acetate than we did acetic acid. So when pH is greater than pKa, we now have more of our deprotonated state, or the conjugate base, and that is something that you should be able to identify in Unit 8. And then, just for added clarification, when pH is equal to pKa for a weak acid or a weak base, just remember that is when the concentration of the weak acid or weak base is equal to the concentration of the conjugate acid or the conjugate base. So that is kind of our reference point to what is then causing the pH to be lower or higher. All right, so at this point, you should be able to explain at the particle level what is occurring when an acetic acid solution has a pH of 5.76 and a pKa of 4.76. So we know that at the half equivalence point, pH is equal to pKa. And we know that means that our concentration of acetic acid is equal to the concentration of its conjugate base, which is acetate. Now, at the half equivalence point, since pKa is equal to pH, we know that the pH is 4.76. So at a pH of 4.76, we have equal amounts of acetate and acetic acid. Now it's asking us to identify what our solution looks like when the pH is higher at 5.76. And because our half equivalence point is here on our titration curve, we know if we're increasing in pH, we are moving towards this region of the titration curve, which means we have more acetate or conjugate base than we do acetic acid. A student pours a 10 milliliter sample of a solution containing acetic acid and sodium acetate into a test tube. The student adds a few drops of bromokrystal green to the test tube and observes a yellow color, which indicates that the pH of the solution is less than 3.8. Based on this result, which of the following is true about the relative concentrations of acetic acid and sodium acetate in the original solution? So first off, some students might be confused on why there's a sodium there. Just remember that we're kind of assuming that this is going to be neutralized with a strong acid like sodium hydroxide. So the real full equation would be acetic acid, HC2H3O2 plus sodium hydroxide, and that is going to form sodium acetate and water. So we're just focusing on the acid and the conjugate base, which is what is shown in our problem here. So looking at our given information, we're given that acetic acid has a pKa of 4.8. We are also given that the solution is at or less than 3.84 pH. So we know that our pH is less than our pKa. So what that means is that our acid or our protonated state is going to be favored or more present in solution, and that is acetic acid. And that brings us to our answer choice of A, because the concentration of weak acid is going to be greater than the concentration of conjugate base because our pH is lower than our pKa. All right, so HCNO is a weak acid with a pKa value of 3.5. The graph above shows the results of a titration of an aqueous solution of HCNO with a 0.1 molar NaOH. Based on the results, the concentration of CNO- is greater than the concentration of HCNO at which of the following pH values? So they make it nice and easy for us. We know the definition of a conjugate acid-base pair differs by one proton. We clearly have our weak acid and our conjugate base here. And we know at the half equivalence point, since the equivalence point is 50, half equivalence point would be 25. Our pH is going to be equal to our pKa, and our concentration of acid is going to be equal to our concentration of conjugate base. So we know at this point we have a pH of 3.5, and we know our concentration of HCNO is equal to the concentration of CNO-. So as we talked about earlier, if we were to go left or have a pH lower than our pKa, that means we're going to have more of our weak acid, HCNO. However, it's asking at what pH are we going to have a concentration greater of our conjugate base, which is CNO-, and that is going to be when we move to the right of our titration curve, or when we have a higher pH than we do at our half equivalence point. So we are looking for a pH greater than 3.5, and there is only one answer, which would be D. So acid-base indicators are weak acids or bases that change color depending on their protonation state. So when the indicator is in its protonated form, it's going to show one color, and then when it changes to its deprotonated form, it's going to show a different color. And this makes indicators really useful for identifying pH ranges and determining their equivalence points in titrations. So the number one thing that I always think about when I'm looking at this is, when we're titrating a strong acid and a strong base, what type of indicator do we typically use in our specific lab? And that is phenolphthalein. But when I look at phenolphthalein, I see that my pH range is 8.2 to 10. So I understand why students are questioning, well, why do we use phenolphthalein even though we know a strong acid, strong base is going to neutralize at a pH of 7? Well, that is a fantastic question, and I want to go over why it is okay to use phenolphthalein, even though the pH range is a little bit off. All right, so in order to understand why we can use phenolphthalein, let's go ahead and break down what's happening in a titration, and this is great practice for calculations for this unit. So we're going to be looking at a titration of a strong acid with a strong base, which is hydrochloric acid and sodium hydroxide. We know that the net ionic equation for a strong acid, strong base is going to be H plus OH minus reacts to form water. And we know this is a complete neutralization. So for 1 mole of hydrochloric acid, we need 1 mole of sodium hydroxide to completely neutralize that into water. So that's going to help us with these calculations. So first, we're going to calculate the pH when none of the sodium hydroxide is added. So all we have is our 0.1 molar hydrochloric acid. So if we have 0.1 molar hydrochloric acid, we know it's a 1-to-1 ratio, so that means we have 0.1 molar H plus ions, and I know that if I have my concentration of H plus ions, I can go ahead and plug that into pH, negative log of the concentration of H plus, which is 0.1. So that's going to give me a pH of 1. Now moving on to what happens to pH when I add 25 milliliters of sodium hydroxide. Well, I know that when I add 25 milliliters of sodium hydroxide, I have neutralized 25 milliliters of hydrochloric acid, which means I have 25 milliliters of hydrochloric acid left over in solution. Now, if I want to calculate concentration of H plus ions left over in solution, I have to first get my moles of H plus ions and then divide it by my total volume. So first getting moles, I know concentration is equal to moles over liters. So if I want to get moles, it's going to be concentration times liters. So moles of H plus ions, and I can do that because it's a 1-to-1 ratio here, will be 0.1 times 0.025. That's going to give us 0.0025. So now that I have moles of H plus ions, to get concentration, I'm going to divide it by my total volume. So I have now added 25 to 50, so I have 75 milliliters, which would be 0.075. That gives me a concentration of 0.33 repeating. So now to get pH, I take the negative log of that concentration, which gives me 1.48. Now I want you to think for a second, a common misconception is if I'm adding half of my strong base to my strong acid, I should be at a pH somewhere in between my starting pH and my endpoint pH, which is 7. So kids assume, oh, I should be somewhere around 4 for pH. But that doesn't really make sense when you think about a strong acid mixing with a strong base, because if half of the hydrochloric acid is neutralized, all I'm left with is hydrochloric acid, which means my pH is going to be very low. And that's what you see here. When I've neutralized half of my acid, I'm still at a low pH of 1.48. So now let's see what happens when we have almost neutralized all of the acid and we have added 49.9 milliliters of sodium hydroxide. So if we have added 49.9 of our strong base, that means we have neutralized 49.9 of our strong acid, which means left over we have 0.1 milliliters of our 0.1 molar hydrochloric acid. So we need to figure out what is the pH when we are literally 1 drop away from our equivalence point. But again, we can assume that we're going to have an acidic pH because we're going to be left over with hydrochloric acid after 49.9 milliliters of it has been neutralized. So first, again, get moles. So we're going to get moles by multiplying our 0.1 molar by our 0.1 milliliter. So it's going to be 0.0001. That will give us 0.00001 moles of H plus ions. Again, I can use that because it's a 1-to-1 ratio in HCl. And now if I want to get concentration, we're going to be dividing that by our total volume. Our total volume would be 49.9 plus 50, which is 99.9 milliliters. That converts to 0.0999 liters. That gives us a concentration of 1.001 times 10 to the negative 4th. So if I want to get pH, I take the negative log of that number, which is going to give me 3.9995, which is 4.0. So I am only 1 drop away from my equivalence point, and I'm at a pH of 4. Now part D says I have 50 milliliters of NaOH added, and I know I'm starting out with 50 milliliters of hydrochloric acid, which means everything is neutralized, so I should have a pH equal to 7 at this point. So now, at this point, we are adding more sodium hydroxide than we do hydrochloric acid. So now I'm going to have leftover sodium hydroxide instead of leftover hydrochloric acid. So I have neutralized 50 milliliters of my hydrochloric acid, which means I have 0.1 milliliters of 0.1 molar NaOH left after everything has been neutralized. So same concept, but now we're going to be solving for OH minus ions instead of H plus. So first we're going to get moles. Remember, that's concentration times liters. And because it's a 1-to-1 ratio, I know I can just use hydroxide here. So that's going to give me 0.0 moles of hydroxide. I need to divide that by my total volume, which is going to be 50.1 plus 50. So that's going to give me 0.101 liters. So that gives me a concentration of hydroxide ions of 9.9 times 10 to the negative fifth. So if I want to solve for POH, it's going to be the negative log of that. So that gives me a POH of 4.00. So if I want to find pH, I'm going to take 14 minus 4. That's going to give me a pH of 10. And finally, what happens when I add 75 milliliters of sodium hydroxide to 50 milliliters of hydrochloric acid? That means I'm going to have 50 milliliters neutralized and 25 milliliters left over. So I have 25 milliliters of 0.1 molar sodium hydroxide. So again, getting moles of hydroxide, I'm going to have 0.1 times 0.025. That's going to give me 0.0025 moles of hydroxide divided by the total volume, which is going to be 75 plus 50, 125. That's me 0.125. That gives me a concentration of OH minus of 0.02. So to get POH, that's going to be negative log of 0.02. Which gives us a POH of 1.699. So if I want to get pH, that's going to be 14 minus 1.699. And that gives us a pH of 12.30, which is when we start tapering off, because now we get to the threshold of our strong base, which is very high on the pH scale. So now let's go ahead and plot all of that math that we just did. At 0 amount of sodium hydroxide, we have a pH of 1, so we're starting here. We add 25 milliliters of sodium hydroxide, and we're at a pH of 1.48, which is about here. At 49.9 milliliters, which is very close to 50, we go up to a pH of 4. Then at 50 milliliters, which is again only the difference by a drop, we shoot up to a pH of 7. And then at 50.1 milliliters, which again is only a drop, we shoot up to a pH of 10. So as you can see, the difference between two drops, we have a pH range from 4 to 10. And then we start leveling off at a pH of 12.3. So our pH curve looks something like this. That's terrible. Let me draw that one more time. Now, we learned in the last slide that phenolphthalein has a range between 8.2 and 10. And the reason we can use phenolphthalein for a strong acid, strong base titration is because that range is still very within the normal limits of this very vertical portion of the titration curve. So yes, it's technically at the end point by 1 drop past it, but since it's only 1 drop, those calculations are very negligible, so we can use them in chemistry labs. and it also helps with seeing that color change because it's slightly past the end point. All right, one more AP chemistry example. A sample of an acid is titrated with 0.1 molar sodium hydroxide. The results are shown in the graph. Based on the pH range of the color change given for each indicator, which of the following indicators would be best choice for the titration? So remember, we want our indicator to change somewhere along this vertical portion of our titration curve. So we are looking between a pH of 10 and a pH of 7. So our answer for this one would be phenol red, because that is changing. It's the only one that is changing within that range of our vertical portion of our titration curve. All right, so at this point, I hope you know that when we're dealing with weak acid or weak base equilibria, that balance between acid and conjugate base or base and conjugate acid is going to be governed by the pH relative to the pKa. If your pH is low, know that your solution is going to hold on to more protons, so you're going to have more of that original acid with your protonated state. If your pH is high, remember that protons are lost. You're going to have more of that conjugate base. Also, at this lesson, you should know that indicators work because their structure shifts with pH. So when pH change at a certain range, they're actually going to change from protonated to deprotonated state, which is going to change their structure and change the color, which is easy for us to identify the endpoint. And then we have our relationships with the dominant species. When pH is less than pKa, you're going to have more of your protonated form. When pH is greater than pKa, you're going to have more of your deprotonated form. And then when pH is equal to pKa, remember you have equal concentrations of your weak acid and conjugate base.